Oh, with the echo. Oh. I don't know where. I have no idea where the button is to shut that off. Let's try this. Okay, and we don't. Okay, thank God, because I feel like I have my own ghost standing behind me. All right, and now I can just project, like you learn on the stage. Right. So today, Carlo Markov chains. So we have gone beyond the normal fit between, like we have a cloud of points, and we fit a line through that. What happens if we think that the noise around a line is no longer neatly random? What happens if there's some like secondary effect that sort of pushes the occasional point away from it? Basically you go, this looks like shenanigans. The moment you go, this is no longer completely random, or I don't trust that this is completely random, or this is a moment like, well, I've been assuming it's random, but should I? Right? That's the point where you go, I am going to make a fit, and then I'm going to have this MCMC approach, which is Monte Carlo Markov chains. There's a reason it says Monte Carlo above it, like it's gambling. It comes from like statistics, but in the casino kind of that way. And Markov chains refers to the way that you walk through parameter space. So we talked about a slope and an intercept, and you do a chi-squared where you try to find the lowest chi-squared. So there's a chi-squared landscape. And let's hope the whiteboard works. No? How about you? See if any of you work. So it's pointing. There we go. So we have slope and intercept. Right, and so we have this is the range this is what I was talking about on last week on Thursday, but I'm realizing I was talking to the void, so I have no idea how much stuck. So we have to choose a range where we think that the slope and the intercept have to be, right? There has to be. So here in the back of our head, we've got our data points, and we want to go fit our model through that, and that means we have a point where it intercepts. Like we have a guess, but mostly like, yeah, it kind of has to lie in there, and the slope has to be positive. So at least it's going up. So positive it is. Like that's already eliminating half the numbers in existence. Great, we're making progress. So those are priors, right? These are things that you decide early on. Priors are, it has to be positive. Temperature can't be negative. If I'm running, I have to, move forward. Although if it's icy like it was last week, that's a non-zero prior. So what you do is you say like, well, here's the ranges that they have to be in. And then you can go, well, I am going to, evaluate it here, and here, and here, and here, and here, and here. And you just plow through, because you kind of go, well, the computer's dumb, so it can do this for me. So it could just go and does a whole grid of that. And then you can kind of make the topology of where exactly is the lowest point for chi-square? Where exactly am I the closest to all my points, right? And you can weigh that with the error. So let's say that's here. And then there's like a number of chi-squares around it, and a number of chi-squares around that, and a number of, like, you get higher and higher in chi-squared. Your fit gets poorer and poorer the further you go away from the ideal solution. Yes? Okay, yeah, nothing more. Okay, so that means I've just wasted a ton of time working on problems that were just crummy fits to begin with. So, but I spent just as much time on this area as I did here. And I'm sort of interested in knowing exactly how wide this oval is, right? I should have been spending my computing time here, not over here. This is boring, not interesting, not where we want to be. So Monte Carlo Markov chain basically says, well, we have a first guess. So this is like the least likelihood method or something like that, where you just go, okay, this is the best-ish solution. And I'm just releasing a whole bunch of little walkers around there, just scattering them around, or maybe also a few over here, just randomly pointing them. And I'm giving them rules. So compute the chi-squared in this solution. I don't know, take a step this way and do it again. Then take a hard left and take a step equally large that way. Is the chi-square still going up? Then take another left. Oh, is it going down now? Great. Now start making smaller steps. Keep taking left turns. Right? That's the simplest possible walker I could come up with. You're just going to have a walker that occasionally takes, a right turn, a left turn. It just sort of stumbles around in the dark, but it has a few rules, which basically say if the chi-square is going up, turn around. If the chi-square is going down, keep going. Now, mathematically, there's like, 24 of those kind of rules. Because sometimes, once in a while, so if you're starting here, you go here, it's like, oh, chi-square is going down, chi-square is going down, keep going, keep going. Whoops, okay, I'll turn left. Better, I'll end up here bouncing around in the information. However, suppose there's a little minimum here. Never mind that this is no longer linear. There's a local minimum. I start here and go like, I'm doing great. I'm starting to really explore here. So there's often a random element to every walker, and that's the beauty of it. That occasionally goes, you still have to do a giant jump once in a while. There's a low odds chance that you do a giant jump, and then you realize, oh, actually, no, this is better, and you end up here anyway. So they're a little random. So when I talked about NumPy random, this is the reason why having a good randomizer is great, because if you know that you're doing the random steps, you can have the occasional random step in there and end up in the right area. So some of them are great with random steps, so they deal well with local minima. And some of them are great for finding the minimum and just exploring that. So it's a little bit of a choice. Now, another thing I want you to notice is that these things then bounce around here a lot. So if I plot where they spend their time, where they end up most of the time, I end up with basically a histogram that looks like this. And if something like that is there, then they spend a little bit of time there. So you end up with, this is called the posterior probability distribution. So I always thought that was a really posterior probability distribution function. I think it actually ends up being PDF. So posterior distribution function. So if I'm being accurate, I always thought that was a really weird name, or just kind of like was this mysterious thing that people started talking about, and it really just ends up like, yeah, this is where you spend your time if you want to spend time in a low chi-squared area. And suddenly that makes sense, because if these things, you can do one for the intercept as well, and so you end up with, do have to use the right one, so you end up with something that goes, okay, only if I draw from here apparently. So you end up with something very similar looking. If they're completely independent and they're completely random, then you end up with something that's a pretty round area here, and you end up with a chi-square, basically with a Gaussian again. And so your initial assumption that a Gaussian was fine, that the errors were that the uncertainties were absolutely random, and a Gaussian is a good description of it, your posterior distribution function being a Gaussian again. And all is well, and you can just do chi-squared, and it's fine. However, often as not, it looks like this. It's almost a Gaussian, so we're mostly fine. But you can sometimes have something that has a long tail. And so if I then do the mean, that's here, and I do the standard deviation away from that, so this is my best fit. That's at the tippity top of that. And end up with asymmetric error bar. The 67 error bar, that's how I think of an error bar. Or the 99%, that's the 3 sigma error bar. So you end up with asymmetric errors, and you can find things where, for example, if this is very flat or banana, you end up with something that is like, yeah, that's degenerate. There's a good fit in this area. Slide this one this way, I have to slide the other one the other way. That means degenerate. Okay, so that was something I wanted to talk to and actually get some visual feedback from people. So if I see some nodding, I'm like, all right, we're there. So that's what I wanted to do. And the nice thing about, is anything happening? No? Yes? Maybe? So the priors is what area do you fit over? And you give every model priors. The fact is that with Monte Carlo, you're sort of very explicit. You say, like, it has to be between here and here. And even with the simplest chi-square fit that we did, we said, like, well, this is the range that our value, it has to be somewhere in here. And it's such a almost unconscious step that you do. I want to be, you want to be explicit about it. Like, this is my prior assumption. I cannot fit temperatures lower than 0 Kelvin. That's my favorite example. So you can have physical things in there. Like, don't spend time trying to fit a model where the universe is less than 0 Kelvin. Those are unphysical anyway. So you can put those priors in. And so we can do that with fitting a line. But we do have we do have to put those priors in, and so you can spend more time. The whole thing about MCMC is that you can high resolution map here, low resolution map there. That was the idea. And so the neat thing is that this is one of those random walkers. This is one of them, and you can see that it has like 2 lines. Like, it has an intercept plot. It looks like to me, it always looks like it's an earthquake plot, but it's kind of over time, just kind of like, yeah, I'm walking around, but I have some internal rules that basically bounces me off like high values of chi-square, and then I go back, and you end up kind of filling in the part that you really want information on. And so the random walkers, that's how I think of them. And you can see that you can even start them at a random place, and it just goes like, well, yeah, no particular thing, so I'll just keep randomly walking until it hits, it's the chi-square is really going down, and then it spends most of its time there. But notice that the posterior distribution there has a tail, like it has a tail on both ends. And so if you want to do this, the neat thing is that this is very easily parallelizable. So you can have one fit with one walker on one, another fit with another walker on another CPU or another computer. And so instead of doing many of one of them, you can do one, you can have it. Walkers, just let them go. A friend of mine told his visual for that is like, you have all the marbles and you just go foomp and just see where they corral in the little pit. So the devil, of course, is in the details. There's always these things where it's like, yeah, what kind of walker rules do I want to do? And the choice of priors is a big one. So if you do that, and you have, for example, these same values, the same model values for 2 different sets of data, you can fit them. You can get like these areas, like this is where my walkers spend most of the time with the black model, and this is where my walkers spend most of the red model, and I can compare them directly. And so you can basically, and you go like, yeah, then the convolution of those are actually where they agree. And so yes, that has my thing. It helps you immediately compare the posterior distributions. So if you have a triangle plot like this, and you will encounter these more and more. This is standard now that we have more computing power. And so you can say, well, here's the posterior distributions for all my my 2 models. And I can say, like, well, here, this one, the red one doesn't constrain it very well because it's sort of like equal probability everywhere. And the black one does. So if I combine the 2, I can actually, I'm statistically more significant. I can actually say, well, this is the value it should have if I combine both measurements. And so I like showing the real-world example, but a good example is, for example, if you have, so gosh, I said example 3 times, 4 times. So if you have sparse data, and sparse data means that there's gaps in your data. We know there's information missing. So it's not sampled well enough to be a Gaussian. There might be a Gaussian with big gaps in it or something like that. So how do I model that? And so that's where this is good. You can use that data, and you can also get uncertainties on your unknowns, on the parameters of your model. The idea. So you can then get a corner plot like this. So there's the posterior distributions. Some of them are neat and Gaussian. They're fine. Some of them are clearly not, or very clearly not, right? So it's already that you can tell that, for instance, these two are this one and this one are degenerate, and this one and this one are degenerate. So you can already say, well, I don't have a very good handle on those. And I can get, which was, you can kind of compare different models, but you can see that even in the log space, the error bars, the upper error bar is smaller than the lower error bar. The lower error bar is literally consistent with 0, but the upper error bar is like we put a very strong upper limit to it, which is very useful if you want to compare that to the models, which also have these sigma distributions. So suddenly you can go like, are we actually comparing the same levels? And yeah, there we are. This is for one galaxy. If I'm being good about presentations, stellar mass. So for a given stellar mass, you expect a certain fraction of the stars to just float around in a big ball around the galaxy. And the model says, well, the bigger your galaxy is, the bigger the fraction also is that is floating around. And so if you do this for the Milky Way, you can count how many are floating loose in space versus the ones that are in the disk. So that's pretty neat. So this is sort of like the next step after jackknifing. Jackknifing and bootstrapping both assumed that the posterior was a neat little Gaussian. And if that's true, this works great. You never have to do MCMC. However, the minute you kind of suspect that there's more than 2 parameters, there might be a third model parameter that you haven't put in there, or I don't think my errors are completely Gaussian. And that's something that you have to be aware of, because, well, if the error bar is a little bigger and you're trying to compare it to like a really critical model, and it's like, yeah, as it turns out, our errors are just on one side is a little bigger. So this is like that model is still completely allowed. And that happens in the real world a lot more. So I'm going to try to do, I haven't got as far as actually executing this. So this is like the how to fit a straight line through points. So we are going to start with data. And once again, this is, okay. Once again, this is artificial data. I have just randomly seeded this, and they have errors. I don't know. You will develop a little bit of an eye for this, but you'll notice that some of them seem to have been jumping up, right, away from the line. This isn't quite Gaussian. And I'm never quite sure how much you can trust your gut in these things, but it is the kind of thing we go like, wow, there's a lot of outliers to the north of this line. I wonder if something's up, right? So that's what you can then do. Is what this is the actual distribution, and then I'll show you what I've done here. Let's see. So I'm giving myself 50 points. I'm ordering that randomly in the extra, and then I've got just an error to go on top of that. And then this is the line, right? That's the line distribution, and then I'm adding an extra fraction to it. So it's like I'm basically adding some extra noise in one direction. I am totally just messing with my own data here. So we do that, and so we can do then a polyfit, right? So initially we go, well, we've got error bars. Those error bars should describe the random noise around the relation, right? There's just an expected level of noise around it, so let's try that. So let's try a polynomial. And that's what we're doing here. And then I'm obviously making a plot. So I'm doing here. I'm doing here I'm doing the polyfit from x and y with 1 degree, and I'm actually weighing everything neatly with my error bar. This is assuming that the errors actually represent the uncertainties in the points, and there's nothing left. There's no extra component, right? So our measurements are true. We should be fine. And so if I do that, and poly 1D is a great way to actually fit it real quick. So we then get this line. This is the polynomial fit, assuming that all the errors are Gaussian and nothing is wrong. Well, for one thing, you kind of go, these error bars are a little small, and about a little over 30% should be off the line so far that even the error bars don't intersect the line. 30% of them. It's more, right? So that's already a bit like, something's off. Like either my error bars are too small, the reported error is too small, or something else apart from the error bar is moving it away from my relationship, right? So shenanigans or underreported errors, both of which can be true. So we compute the chi-square for that, right? So you can. Is my solution, or is this? Yeah, this is the solution. Anyway, this is you can compute the chi-square for that, and then also you can just say, hey, I've got my measurement, and I am going to do my uncertainty. For one thing, this doesn't look terribly Gaussian, right? I'm actually making a histogram of how much deviation I've got. And the orange bar that I've just plotted there is just to show what the expected average uncertainty was. So if everything is fine and your uncertainties reflect the uncertainties in your measurement, there's nothing else going on. There's just some noise in your measurement. And remember, we can never get rid of it because we are experimental people, and so there's always an uncertainty in your measurement. And so you look at that and go like, well, that's the width of the Gaussian that I should be seeing. But I don't see that at all, right? I've got something that looks kind of Gaussian, but it's way fatter than it should be. And it's even got a bit of a tail to one end. So what's going on? So something else, this is not Gaussian, it's not well behaved, something else is up. So how do they compare? So you can get the least chi-square, so you can do the least square fit. And that sits right on top of it. Yeah, it's sitting right on top of the polynomial fit as well. So I'm fitting, now I'm just going like, well, these errors are just silly. So I'm going to ignore the errors. I'm not even weighing everything. So I'm just going to see what happens if I just do, minimize the distance between all the points in my model. And that's what I get. And so as soon as those two start agreeing too much, then you can also go like, well, something must be up. Okay? So you can do the chi-squared again. And so you sum the difference between the model that you've made and the data, and you take you sum them quadratically, and you weigh everything by the error quadratically. And so you end up with high chi-squares. Okay, fine. So now I'm doing something called a maximum likelihood fit. So instead of doing minimizing a chi-square, I'm saying this is what's the likely good solution. And it takes a little while, but you can do this here, minimize function. And it will take, you have this function defined as like, here's my, out of theta, I'm actually getting the fit parameters. Then I make a model, and then I'm actually returning the inverted chi-squared. And here is like this likelihood that this is the right model. And I can model over that. And then if I plot that, you'll notice that it's a little different, but actually closer to the dashed line, to the truth here. So if you do a maximum likelihood, that's already going through and not assuming Gaussian distribution. It's rather agnostic on that. So it just goes, okay, what's the highest probability of all the possible solutions that, that this is the right model. So it's already doing a better job. So we can actually compute the chi-squared. Let's try that. Here's the chi-squared 1. And we need the poly 1. Where are you? This is the maximum likelihood. This is the chi-square for the maximum likelihood. Where did we get all of them? Yeah. So here we are. So we got the chi-square from the polyfit, from the least linear regression, and the maximum likelihood, ML, right? So all of three have a different chi-squared. So they found a different minimum. The first two agree with each other. The second one actually has a different value altogether. It's in a different spot. So maybe the chi-square is actually not telling us everything here. What happens if we remove the additional uncertainty? So if I go up here and here for question 7, I remove this extra bit. If I now turn everything back into random noise, everything agrees. The chi-squares are super low. That's because there is no extra component anymore. See what I'm trying to do? Is everybody sort of like following along? Okay, great. So that happens if I don't have that extra uncertainty, if I don't add more than I should have there. So putting it back in. Oh, I went a little too quick. I wanted to show you one more thing. Look at that. Now, from the histogram, I can't tell if the distribution is really Gaussian because it's sort of clunky. It's got a few big steps in it, and it's rather big ones. But the uncertainty, the standard deviation, is very consistent with the mean is at 0, and there's a standard deviation. Those distributions look about equally wide. So my measurements and the residual from my model agree. See where that's going? So if you got a measurement and your machine says, this is the standard deviation of your uncertainties, and then you fit a model to it, and your residual has a Gaussian distribution with the same width, you go like, great, I've explained the whole thing. You got a question?
When you end up with a histogram that looks like that, is it better to try to increase the number of bins, or will it not really change?
Right, so going back to, if we make histograms, right, we bin the data by definition. I am just sort of like, I am doing literally telling Matplotlib nothing about what I want here. I'm deliberately just having it choose for me. However, as soon as you see something like that and you go like, well, it would be nicer if I'd had like a little bit better of a feel, so maybe I should increase the number of bins. Absolutely. People say like play with the number of bins. I mean, honestly, I'm like, if I do that, this is too many, because literally as many as there are data points. So I can go, well, 12. That's sort of what I just got. 20, getting better. Honestly, you can kind of go back and go, really, if I want to see that properly, where's n? Here's n. I'll go here. I would like 150, and then you can go, yeah, no, 50 is a bit too much, 30 maybe, and so you can get a feel for that. But even then, since this is still 150 is only barely above low number statistics. Low number statistics start at anything below 100. That's sort of the local definition. But here you can already see it's like, yeah, it probably is a Gaussian, but I'm having a hard time because I still don't have enough data points to really see that, right? So what I should be doing for that, you can always, this is the sort of, you can tell that I'm an astronomer because our favorite way to solve the problem is to whack it with more data. So you can always go, well, fine. 100 was fine. Let's do it for 1,500 and just get out of the woods. So now I'm going like, yeah, that's a Gaussian. Fine. But if I do that, then the actual MCMC model takes forever. So I'm going to go dial it back down to sparse, because that's what we were talking about, right? If you're in that low number statistics, sparse, maybe there's some gaps in my data, plus there could be an additional component moving points away from my model. Let's see what that looks like. So back to 50, and also back to having shenanigans in there. Whack, 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 whack. So we can jackknife this, right? And then we get a different, or we can bootstrap this, and we get these values for the slope and the intercept, and also, and so we can actually see what that looks like and compare that to our true values, the ones that we set out to do before. So let's see, boo. So what we need for that is something called MC. And now, because I will show you briefly how to install that. So, it didn't have that, so I need to go and install that. There. So you do pip install MC, and then hopefully it works. So let's see if that worked. Where am I? P390. So I am totally Martha Stewarting this and going like, yes, I actually have a solution, right? I'm not typing all this stuff in. I realize that this is going maybe a little fast. Oh, I've got way too many here. 1,500 is a bit much. So back to 50 and adding that extra component. I can do polyfit, but the histogram looks circumspect. Even if I do 12 or anything like that, it doesn't look terribly Gaussian. I can do a least square fit. That gives me a chi-squared. I can do a maximum likelihood, and that gives me a chi-squared. And all three of them don't seem to terribly agree. And I can also do this with jackknifing and bootstrapping, and it gives me uncertainties. And that looks OK. But notice that this gives me like a slope of minus 1.2 plus or minus 1.1. It's not really in that range, right? The actual true value is lower. The intercept, same thing. Like you're really not in the right range. You're not only getting it wrong, so that extra push for the occasional point to be far away from your line is throwing off any kind of fit that you're having. It's really messing with your model. It doesn't sound like, oh, it's like, well, there's a little bit of extra noise. Like, no, this is not it, right? It's really just kind of weighing your model the wrong way. And now that doesn't sound too bad because it's behind the decimal point, But if you're a physicist or an astronomer, you care about stuff behind a decimal point. In fact, your entire PhD might be happening beyond the decimal point. So this is the part where it's like, yeah, I have, looks believable, right? I've got a slope and I've got an uncertainty. But that uncertainty assumed that this was completely Gaussian. That uncertainty assumed that it was a neat distribution and there was no weighting one way. And there is, right? So the whole thing has shifted with respect to what the true values were. And I know what the true values here because I gave it at the beginning, right? My slope and my intercept are like, those are I already know those, and I know how much of a fraction of data I have messed with. So that's the other thing, that F true is the fraction of data that I have just, futzed with a little bit. So that last parameter is something that MCMC minimizes over, right? So it gives you a fraction of like bad data. It gives you a fraction of how much the data has been deviating. So, whoop. Yep, here we go. So what I now do is I've defined this probability and I've given it a prior. So the prior, very importantly, tells you that the slope has to be somewhere between -5 and 0.5 and the intercept between 0 and 10. That's something we did with the chi-squares as well, right? We kind of go like, spend your time here. This is your playing field. Don't wander away. It's almost like having kids. Don't wander away from the monkey bars, because we know it has to be in here. And if it's basically wander outside and you give back infinity, just go like, your probability just went thunk, just set it to 0. There are also priors where you go like, yes, well, I said that we shouldn't play right outside the monkey bars, but as it turns out, there is a soccer field there. So just on the off chance that there is a reason to go out off the boundaries, I'm not going to set it to -infinity, but I'm just going to set it to like a millionth. So you really have to get a great reason to move out, but you can set it to non-zero. So that's another way to do a prior. A prior doesn't have to be a cliff. It can actually be a function. Yeah, we go like, yeah, just make it, just gradually go to -infinity, or just gradually go to, just keep weighing down as moving out. Okay, so what we then do, here's our position. We do a random number. We do 5,000 steps of MCMC. We do a whole bunch of walkers. And as you can see, it walks all of them. Okay, let's see if that works. So remember that earthquake? It's now doing that for the slope, the intercept B, and the fraction of stuff that has been messed with the log of it, right? So you can see that all these walkers have now simply walked, bounced around, and given me where they like to spend their time. So you can kind of see, like, yeah, they may have all started here, and then they just will spend a lot of time around, and then there's like a medium here. Okay. So then, it doesn't exist anymore. I may have to do this again, the corner. Sorry about that. You also have to do there. Back to the Dropbox. So So this is completely based on this one example with MC, which again is fitting the line. It's everybody's favorite thing to do. Where are our samplers? Here we go. And so now we plot the distribution of the three things, like of the slope, of the fraction, the fraction of bad data, and we can see where they're like these two are pretty degenerate, the slope and the intercept. Yeah, we knew that from the earlier fits, and we can see that the other ones are independent, and we can see their posterior distribution. I mean, they're very close to Gaussian, but definitely has a tail. So suddenly you can realize that you can model these things and get an uncertainty based on the number of where the walkers spent their time, but also you get a like this is the weight, the mean weight, like this is where they spend most of their time. This is the best solution for this. And so you can plot the maximum likelihood values, and with those values you go, okay, well, what does that look like? So not only do you have an uncertain, not only do you have like a best value, but you have like how many of them are around that, and it gives you an uncertainty for both plots. Okay, so this is a better way to do things simply because you explore your entire parameter. You have something explore your parameter space, and you have to have something explore your parameter space efficiently, rather than going, well, here's my n-dimensional parameter space. It's infinity in every direction. Compute everything with a 0.1 step through everything. That's A, never going to end, and B, why would you do that to yourself or your computer? This actually is an efficient way to find the area that you want to be in, have the walkers there, and it also gives you, so it gives you that extra component, which is that fraction of values that are off, the fraction that is bad. I don't want to say bad data, but data that has an extra sloppiness to it. And so you have an uncertainty, but notice also that these uncertainties are slightly asymmetric. So instead of having just kind of cramming everything into a Gaussian, because that's a forceful assumption that everything that is left over is random. And it doesn't need to be. There could be secondary effects. Einstein's general relativity is a secondary effect on Newton's gravity. So, secondary effects are going to be interesting. Secondary effects are going to be there. And so fitting that helps. Fitting that allows you to see where your range really lies, rather than forcing it, ramming in that Gaussian through, and saying it has to be this symmetric Gaussian. It doesn't have to be. In fact, if you're dealing with physical systems, odds are it probably isn't. So this is kind of revolutionizing how physics and astronomy are dealing with like multi-component parameter space, and how they're dealing with multi-component data. Because hey, it's not just a line anymore, right? So you can expand that and fit your data. Okay, well, that was my 2 cents for the day, and I am now very hoarse. So MCMC is straddling that bit between everything is neat and Gaussian, and I have a model that I can fit to my points, and whatever is left is a Gaussian. It's just random noise. That can be assumption, and then you can also go, I'm letting even the model go, and giving the computer just a bunch of options it could possibly fit, and it will go and learn itself, like the walkers, what kind of model should be there. In fact, that becomes so opaque that it is this mystery step where I'm just the computer is just optimizing to go from data to output that we wanted or output that we flagged, and it does these randomized steps until it optimizes and always gets the answer right, and that's machine learning. So this is sort of like the step in between. We are going from all our data is neatly randomized and noise is all Gaussian, to, well, maybe all noise is not Gaussian. Maybe let's get closer to reality, to we're modeling it in a way that we're actually left the model to the computer. So this becomes this black box, and we sort of a posteriori describing how it works, or we've basically taught it how to classify things. And that's what we'll talk about Maybe I'll start next week, but next week I want to talk about the final, because this class does have a final. It's a very small one, but it does have a final, and so I want to talk about that next week. And then we have spring break. So, and then after that we go basically into the machine learning bits and bobs. Yeah? Cool. Okay. Works for me. What time are we talking now? Oh, perfect. Yeah, I can't talk more than an hour, so that's... Any questions about this? I cannot emphasize, like, we had this really gappy data. The data was more gaps than actual data, but we had data. So this was the Hubble space. I will talk about this for 10 minutes if you'll permit me. This is extra time, yeah? So the thing about this was, you think Hubble pictures, but it's very hard to picture how big a Hubble picture actually is on the sky. If you want to know how big a picture this thing actually is on the night sky, you take your arm's length, you take Lincoln's eye, and that's how big this thing is on the sky. It is minute. I've had questions during public talks, for example, like why do like the entire night sky with Hubble? It's like, cool, yeah, no, just give us a million years or two. It would take forever. So we have these like really sharp pictures, and they're sort of like they're just like a Lincoln eye here and here and here and here and here. Like there are really little bits left, right. It's like, so really sharp. We know everything along one line, but everything around it we don't. So that's really sparse sampling. That's basically, I know there's a star here, and I have to infer the existence of the rest of them. I know there's a Milky Way, like that's as far as I got, right? And I know there's a center of the Milky Way. But we only count stars at very randomized points. This is not a census. It is state proof. So it's like randomized sampling, right? So it's sampling, not a census. Like I don't count all of them. I just count at random positions. The random part is important because basically then I can say, well, if it's random enough, this should be representative. It's really gappy, but it should be representative. So then you can go through and say, like, well, if I take a census of the halo of our Milky Way, then I've got a model where I can say, like, well, as a function of radius and height above the disk of the galaxy, there has to be a certain central density. A fraction of that is in the halo. A fraction of that, the rest of that is in the disk. The disk has a certain scale height and the scale length, and those are my parameters. So I can fit those parameters to my super undersampled data. And just to give you an idea of how undersampled it is, astronomy is great at undersampling things, right? As soon as we get started, it's like, yeah, I only have 270 stars here, 274. The number of stars they inferred from the data was, I think, 59 billion. So if you 58 billion. So if you integrate that model, and you say, okay, how many stars did I infer in the disk and the halo total? So you integrate your model over your density of these kind of stars, right? These are the piddliest, smallest stars. You can only pick them up with Hubble, really, at any kind of distance. So they're called M-dwarf stars. How many of them were there? There are 58 billion of them. We inferred that from 270 stars because it was randomly enough. We also got that with a number uncertainty that was actually pretty good. That's a quarter of the stars in the Milky Way. So that's very good, and especially since your data is pretty gappy. So if you kind of go, well, I've sampled randomly enough, right? Other example, how many people are fans of the Cards? If I go and ask everybody who comes out of the stadium, going to be 100%. If I'm at the wrong exit, it's going to be 0%. But I'm not random sampling. Now, if I go to Kroger and just ask everybody who comes past the cashier, hey, are you a fan of the cards? That's much more random sampling. Make this even more random, right? So yeah, I'll just randomize which Kroger I go to. Can I even make this more random? Like, yeah, not just, I'll just go every third house in Kentucky, and I'll get a much better, like, but that's a bigger and bigger thing. Like, if I make sure that I'm super random, and there's no hidden, like, where I'm asking is a problem, then yeah, I can have very sparse data and infer the actual value from that. And MCMC is one other way to do this. Okay, well, okay, that's me off my soapbox. I am done. I was super proud of these two, and Wade, who did a very similar, like, tricky thing with MCMC. So yeah, this is a good way to work. And MC, you saw how easy the installation was. It was pip install MC, and I've got it, right? So there's all these wonderful examples. So this was just one of them. And then you can get these models. You can get a model to work on your weird, wonky data. And you can compare your different models as well, how well they're doing. OK. Thanks for coming. Are there any questions about assignments? I will grade them as soon as I can. If you are getting stuck on them, put them in anyway, because they don't have to be perfect, but I would like to see your work. If there's stuff that's unclear, if you're kind of like, I get stuck on this because I'm not sure what you want, sir, here, put that in, because I've made quite a number of these new, and I'm very curious how I'm doing, and I'm sure I've messed up somewhere. So please, give me feedback if you put them in. All right, Wade, you had something?
Yeah. Question. See, I'm doing the chi-square.
So you have do you have a model?
Here we go. So I was trying to define like a chi-squared function, basically. So just taking the sum of
Okay, so
y and y true.
y true is the yeah. So but we want our model, right? We have a polyfit model, and the polyfit slope, etc. are print the fit, or like that's the. Here we go. So that's fit 0 and fit 1. This is the intercept. That's the slope, right? So those are the ones that you need to use. So your y fit is y minus y fit. It's the data minus the model divided by the data. That's your chi-squared.
Okay.
And I strongly recommend that you just go like chi-square and then like, I don't know, dash PF or something like that, so that you remember which chi-square this was. So because you can then compare it to the other ones later.
Okay, that's PF.
Yeah, or whatever you want to call it, like, or polyfit chi-squared or something like that, right?
The other thing was on notebook 12, we don't have this data file.
It's on Blackboard now. I am so sorry.
Okay, no, that's fine. I just skipped it because I couldn't find it.
Nope,
Yeah.
it's on there now.
All right.
I'm struggling.
Okay.
Mostly, to be honest, I think I've turned into 2
Yeah.
assignments. But I plan to get them done this week, the ones that are due so far.
I'm trying to make it so that if you go like, okay, like if you're running into something like, nope, do what you can. I sincerely try to make some things skippable, but it's kind of hard with programming because it sort of builds on the rest. But if get to where you get and then hand it in, because then I'm trying to make them as independent as possible. But once again, everything builds on everything else, so it's painful to try that, but try it. And hand it in because I can create anything that I don't have. So my math teacher had a fantastic, please make errors in the things you don't know. And everything else, please put that on paper so that I can grade it.
Okay.
So that's my attitude here.
Okay.
Yes, sir. Yes, ma'am.
January wanted me to tell you that she was having a panic attack, and that's why she had to leave.
That's okay. Yeah, I would like her to. Okay. Oh, this is not being recorded, so I'll cut that off, I guess.
Oh, I'm sorry. I
No,